Welcome back. We are now ready to start talking about the linear algebraic, or what was sometimes referred to as the vector or the matrix vector solution of simultaneous linear equations. So the first thing we're going to do is to just talk generically about vectors and matrices, the building blocks of the machinery that we use in linear algebra, and then we'll get to talking about how you use that machinery to solve these linear equations. So remember, again, we have two linear equations, x and y. These are linear because these are only being added to each other and scalar multiplied. And we're going to represent these equations a little bit differently. And to do that, we've got to talk a little bit about vectors, vector addition, vector multiplication, matrices, matrix multiplication. And once we've done that, then we can start talking about the solution. So let's introduce the notion of a vector. There's nothing fancy about vectors. It's just a different way of representing a point in a 2, 3, 4, 5, 6, whatever dimensional space you want. So typically, for example, when we plot a point in R2, the real values on a plane, we say this point here is 2, 1. So the first value is how much you move along the horizontal axis. The second is how much you move along the vertical axis. And that's the point 2, 1 in a Euclidean space, extremely familiar to all of us. I refer to the vector as the arrow starting at the origin, moving out to that point as the slightly different notation. This is what's called a column vector because I'm arranging the points top to bottom versus a row vector side to side, and I simply stack the values on top of each other. It corresponds to more or less the same thing. I'm going to now, instead of talking about it as a point, I'm going to talk about it as that line starting from the origin going out to some point. What is that point? It's the point 2, 1. Okay? So similarly, this is the vector -1 horizontal axis, +1. Again, it's a vector, it's a line that emanates from the origin to that point. And again, we will refer to this as a column vector because I'm going to stack the horizontal x and vertical y values on top of each other. There's also, eventually we'll see our row vectors, which is just that rotated so that it's -1, 1. But for now, let's just stick with column vectors to represent points in this space. This is the vector 1, 5. 1 on the horizontal, 5 on the vertical. Now, I can scale vectors. So if I give you some point and I want to scale it, what does it mean? You just multiply all these values. So 2, 1 doubled in size is the vector 4, 2, or the point 4, 2. And I can do the same thing here. So if I want to scale this vector, I can multiply it by some scalar value, which simply means I scale it along the direction. So this vector 2, 1 scaled by 2 simply means you're going to multiply both components by the same scalar value. So 2 becomes 4, 1 becomes 2. And of course, what I'm doing is I'm preserving the ratio between these. And if I'm preserving the ratio between them, then the angle here can't change. So it's simply sliding along that line from the origin to where I was before by some scalar amount. So here I've doubled it. You can see the vector is twice as long. I can scale by a negative amount. So if I multiply this vector by -1, I negate these values, and then I flip around the origin, and I have the inverted vector -2, -1. I can scale by 0. I can collapse that down to nothing. So if I scale by 0, then I get the vector 0, 0, which we just represent as a point at the origin. So here's the rule for vector multiplication. A vector, again, in a two-dimensional space is simply a point in a two-dimensional space, which we will think about as that arrow, that vector, moving from the origin to that point. We stack the values into a column vector, x, y. If I want to scale that vector by some amount a, well, that is the same as multiplying the x component by a and the y component by a as well. By the way, this will hold for arbitrary dimensions. So if I had a three-dimensional vector, x, y, z, scalar multiplication is ax, ay, az. If I have a four-dimensional vector, w, x, y, z, then the scalar multiplication is aw, ax, ay, az. So I'll do everything in 2D because we can visualize it, but everything we'll talk about here generalizes to arbitrary dimensions. All right, that's vector scaling. We need to be able to do one more thing to eventually be able to solve simultaneous linear equations, which is add two vectors together. Okay? So if I have the vector 2, 1, 2, 1, and I have the vector -1, 2, so that's those two vectors there, and I want to add them together, then the way to do that, there's a geometric picture and an algebraic picture. So the geometric picture is what is the so-called head-to-tail construction. I take this vector 2, 1, and I plop it down right up here. So you can see that that vector there is the same as this. I've just moved the origin so that the head of the vector 2, 1 is at the tail of the vector minus 1, 2. So head, tail. So 2, 1 goes there, and then I take this vector and I do the same construction. I just slide it over here, and then those two will meet at a point, and that is the vector sum, or the vector addition of these two. Notice, by the way, that this vector, which is 1, 3, is equal to minus 1 plus 2, that's 1, 2 plus 1 is 3. So vector addition, like vector scalar multiplication, is pointwise addition of the x and the y components, but it has this nice head-to-tail geometric intuition that you can have as well. So we can see it geometrically and algebraically. Okay, one more example. Let's sum these two vectors. So there is I'm going to take this vector here and I'm going to draw it right there. I'm going to take this vector, draw it there. There's the head-to-tail construction. That vector is now the sum. So this vector was 2, 1. This vector was 2, 2. And the sum is 4, 3, which is just the pointwise addition of the x and the y. And again, this generalizes to arbitrary dimensions. If I had a 3 vector here, I would just sum, sum, sum. If I had a 4 vector, sum, 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 sum. So here is the rule for vector summation or vector addition. I give you two obviously the same dimension vectors, x, y, and u, v, and the sum is simply the sum of x and u, the sum of y and v, and down the line if you have higher dimensional vectors. Okay, now let's put all that together into one concept, which is the linear combination of vectors. So the linear combination says you are allowed to add things and multiply them by scalar values. By the way, that should sound familiar. When we were talking about simultaneous linear equations, what did I keep saying? Is that you're allowed to sum the unknowns and scalar multiply them. And that's what we're doing now, but just in a vector space. And you'll see in a little bit why we need this. But that's a hint as to what we're eventually going to do. We're going to formulate the linear equations in this type of linear algebraic framework. All right, linear combination is I can take two vectors, obviously of the same size. I can multiply them by scalar values, and the result is this. So let's just work through the pieces of this. So a times xy is ax, ay. So you take that scalar value and you multiply it by all the components of the vector. B times uv is equal to bu, bv. You take that scalar value and you multiply it by all the components. And if I have ax, ay here and bu, bv here, well then the sum is simply ax plus bu, ay plus bv. So pointwise multiplication is you simply multiply everything. Scalar multiplication, rather, is you multiply all the components of the vector by the scalar. And addition is you pointwise or pairwise sum all of the components. Okay, that's the basics of vector. We know what a vector is. It's just a point in a high-dimensional space. 2 dimensions, 3 dimensions, 4 dimensions. We just sort of think about it and represent it a little bit differently. Instead of putting it with the commas for all the various dimensions, we stack it into a little column vector. We can scale that vector by sliding along the line. We can sum the vector. You can think about that head-to-tail construction, or you can think about it algebraically. And why am I doing that? Well, because eventually what I'm going to do is take those linear equations, those simultaneous linear equations that I want to solve, and I'm going to use this notation to represent them, and you're going to see that that turns out to be a very powerful framework for thinking about simultaneous linear equations, and then more after that. Okay, so we got a little bit more to do with vectors and matrices and the building blocks of linear algebras, and then we will get to actually using that machinery to solve the linear equation. So I'll see you in a few minutes.